Hello, let's make a first-person... hang on, scratch that. Let's upgrade a first-person shooter game.
Now, long-time supporters of the channel will realise that one of the first videos I made was a first-person shooter engine at the command prompt, and I think it's time to revisit that now that we've learnt a few new things about how to use the command prompt in a really graphical way. So here I've upgraded the first-person shooter engine to include textured walls and sprites, and we can now also fire bullets and move around and strafe, and we're getting closer to having a working full featured first-person shooter engine. I've also made the map much larger so we can explore a bit further. And so this video is really going to be about how do we handle the textures and how do we handle things like the Z buffer that's required for us to draw objects on top of other objects. I should stress that this video is not going to go into the raycasting techniques used to generate the 3D world. We've already talked about that in the first video, and this is no different in this video.
It shouldn't be surprising that with the introduction of texture we can make the worlds a lot more immersive. So let's see how it's done, but I'm going to start with the original code base.
I've loaded up the original code base, and I think it's worth pointing out that this doesn't use the console game engine. However, it should, so that's the first change I'm going to make, is to port it over to use the new platform. That way it stays in keeping with the current track of most of my videos. Fortunately, this won't be too difficult, because the console game engine was actually just to wrap up the common functions that I use in this first-person shooter, such as creating a screen buffer, and drawing to the console as well. Another difference is how we handle the input, and here I'm using getAsyncKeyState to directly access the keyboard buffer. Of course, this is now also handled by the console game engine.
So now it's time for some creative copying and pasting.
So the first thing is to actually include the console game engine.h file. This includes the other includes that we'll often need. And we'll see that a lot of the code is just floating around in space. It's not owned by a particular object, and the main function does the bulk of the work. So we'll need to create a class, which inherits from the console game engine. And I'm creating a class called Ultimate FPS, which is the second in the series. And we've got a constructor by default, but we also need to give it onUserCreate and onUserUpdate functions. Let's just fill these in for now. Now all of the global variables before, I'm just going to cut out of the global space and paste them into the private space of the class. But I'm not going to need screen width and screen height. We have functions for those. I know I'm not going to need a screen buffer anymore. Now the map, this also happens before the game loop, so we need to add that to the onUserCreate function. We see there's a variable which we'll need to add to our private space. So I'll take the map initialization code and paste it directly into onUserCreate. Timing and control for felapse time is now handled by the game engine, so we don't need any of this. In fact, let's start getting rid of it. And this leaves us with our input handling routines. I'm going to copy these and paste them into the onUserUpdate function. But we do need to make a slight change. Instead of calling getAsyncKeyState directly, we're going to use the mkeys variable. Be held. And we'll make a similar change for all of the other inputs. The original algorithm rendered column by column. We're going to do exactly the same, so I'm just going to take all of this code and paste it in. But I do need to make some cosmetic changes, so instead of screen width, we're going to call the screen width function.
The Visual Studio environment can be quite handy for refactoring code like this, because it does this real-time compilation of the code. It highlights where the errors are. So by taking out the endScreenWidth variable, I get little errors to flag, and that shows me all the locations that I need to change it. Of course, I could also use some of the built-in refactoring tools, but I still like to do things manually. I'm old-fashioned.
So we'll change our screen height variable to, of course, the function equivalent. And we can see on the right-hand side of the screen that as I fix the errors, the red dots move down and shows me where the next error is that I need to fix. At this point, I'm also going to take the displaying map and player routine. So I'm just going to take that out of the now junk main function and paste that back into our onUserUpdate function. But you'll notice we've still got quite a lot of errors, and that's because of this screen variable is no longer valid because we have the draw routines now. So wherever we see a line like this, we know we can replace this with the equivalent draw function, which will just be draw x, y, and in this case it was drawing a space. And we'll just make sure that we use a wchar space. The same, of course, applies to our map as well, and our player location. Where, don't forget, the map is drawn offset one character in both axes from the top corner. This just makes it look a bit tidier. Now, I'll just get rid of these brackets, we don't need them. Keep the code concise. So this just leaves us with our int main function, which is now empty. But of course we have to create an instance of the class we've just created and construct the console. In this case I'm constructing it to be 120 by 80, which tries to reflect the original console, and I start the game. So just through cut and pasting, let's see how that all looks. And what we can see is we've got the very first console game engine first-person shooter thing, which is still working very nicely. Good. Now that it's easier to do, and out of curiosity, I'm going to set the screen of the game to be a much higher resolution. We know from the webcam that 320 by 240 by 4 by 4 is an acceptable resolution. Pixels begin to look like pixels, and everything still runs at a sensible speed. And we can see that the game does too. The frame rate has dropped somewhat because there's more calculations to do, and the console has a more complex rendering task, but it still works. It's still nice and smooth, and the high resolution means our edges look less jaggy. The original map is a 16 by 16 matrix. I'm going to replace this with a 32 by 32 one to give us a much larger map, but I also need to update my map width and map height variables. Having a larger maze allows us to test two things. Firstly, does the rendering algorithm still work trying to draw over greater distances? And secondly, when we start implementing more exciting features such as enemy AI and rendering of sprites, do they interact well with the depth of the screen? It's also just cooler. It's a bigger maze.
The original video didn't implement strafing, i.e. moving sideways, and it was left to the viewer to implement that for themselves. And some did, and left some comments, and so I've just included that routine into this new video.
So here where we're handling forwards and backwards motion, I'm also going to handle sideways motion. And it's exactly the same looking code, except the only difference is I'm playing a little trick with the trigonometry. When we're moving forwards and backwards, we use sine and cos both in the correct direction. So in this case, to move forwards, we add both the sine and cos of the player angle to the current player position. To move 90 degrees to forward, we can simply invert one of the sines and the coses. And it turns out that to strafe right, we invert the sine, and to strafe left, we invert the cos. I've mapped these to the Q and E buttons. Let's take a look. So now I can move sideways and forwards and rotate.
It's a really nice effect.
Now when we're working with sprites, it's much more convenient to use a sprite editor than to try and define everything in code. And I've used a sprite editor before when I created my Code It Yourself Frogger video, so I'm going to use the same sprite editor here. And I've primed the sprite editor with a 32 by 32 pixel sprite, and I'm going to call it Wall1. Now there aren't any nice user features of my sprite editor, so the only way to run it is to actually run the code. And then I'm going to load the pre-existing wall sprite that I've created. So I can zoom in and I can control a cursor and change the sprite as necessary.
The sprite is really just two 2D arrays. The first contains the symbolic information, i.e. which font symbol should we use at that particular location, and the second, in a corresponding location, defines the colour.
And so I've used the sprite editor to create a wall texture. I've decided to upload the sprite editor code to the GitHub repository so you can get it and play with sprites yourself, but the thing to remember is you still have to initialize them in the onUser create, including the file name that you want to save it as. Most of you will be familiar that a sprite is really just a 2D image, and it will have a width and a height. And we usually index from the top left corner, so this would be 0, 0, and this would be WH, width and height. But it's common practice with sprites and textures to normalize this, which means we can specify any pixel within our sprite to lie between 0 and 1. And so if I want the pixel in the middle of the sprite, I know that this is 0.5 and 0.5, regardless of how big the original image is. And this means I don't have to have lots of constants and scaling coefficients stored in my program. The process of getting a colour at a particular location is called sampling, and it returns the sample. And I like to think that sampling also encompasses this normalized space, so it becomes a very simple calculation for the sampling tool to do. In this case, if I want my sample to be 0.5, 0.5, then the actual coordinate, the physical pixel in my image, is just my sample position times the width, and the sample position in Y times the height. And this gives me the location in pixels. And it offers many advantages. So let's say, for example, I want to sample my texture at 1.25. Well, if my sampler knows to just always ditch whatever is at the front and only use the decimal portion, then it wraps around. So it'll go across the bottom and back in again to 0.25. And this makes repeating textures very simple. Another advantage of normalizing the coordinates is it doesn't matter what size my texture is either. So I can use a 32 by 32 pixel texture, or I can use a 16 by 16 pixel texture. I don't need to change my code. The sampler will handle all of the conversions necessary. The console game engine already contains an object called OLC Sprite, which we've used in several videos in the past. And this object contains the functions getGlyph and getColor, which take integer arguments. I'm also going to add sampleGlyph and sampleColor, which take floating point arguments for our normalized space and do the conversion. Although in this instance, if you sample outside of the sprite area, it's going to return blank. The raycasting engine works on a column by column basis, and it determines the columns based on the field of view from the direction that the player is currently looking. So I'm going to draw in a field of view as these green lines here. And just as a quick reminder from the first video, we essentially try and work out what is the distance by incrementally creating and testing a line. What is the distance along one particular column in the field of view to an obstacle? And when the line hits an obstacle, we know that that distance is there, and we can use that to calculate the depth on the screen. And we do this for all columns, fanning out at a step-sized angle to work out the depth of each column. And this worked very nicely because the walls weren't textured. It didn't matter where we hit them, it just mattered that we hit them. But now we want to sample from a texture, we actually need to know whereabouts we have hit the wall. So we need to know what this coordinate is to get our sampling point. And I'm going to make an assumption for my game engine. We already know that all of the cells are 1 unit by 1 unit wide. And I'm going to assume that 1 unit across is equivalent to 1 texture. So in the case of my 32 by 32 wall, that's the equivalent of my 1 32 by 32 wall segment going across. So given that scrolling through the field of view in this respect gives me my x coordinate, in column space for the screen, I need to work out where the x-coordinate is for sample space of my texture. And it turns out that this is actually quite tricky, because all I have is a Boolean flag to say whether a wall cell exists or it doesn't. I don't have any geometry information in any of this at all. Determining how to sample a texture isn't that easy. For example, assume the player is stood here. I know when I'm casting the ray out, I know what the distance is, and I know what the angle is. And so it stands to reason that I can calculate the coordinates of this collision point, x and y. Knowing that my cells are all unit in size, so 0, 1, 2, 3, whatever, I can ditch the 0, 1, 2 and 3 and just use the decimal as the sampling coordinate for my texture. So in this case, let's say it looks about 0.4, I can pass the 0.4 directly into my sampling routine to tell me how far across the texture do I need to go to sample it correctly. And that's great, but it's not true for all cases. So let's assume I've got the same distance and angle now, and I can calculate the collision point between the ray and the solid cell. But this time, it doesn't matter where, the x component doesn't change, and in fact the y component should be used to sample across the texture. And so depending on the side of the cell that gets hit by the ray, we need to change our sampling approach accordingly. Along the bottom here, it becomes plus x. If we go along here, it becomes plus y. Then along this edge, becomes minus x. And along this edge, finally, minus y. Therefore, we need to know which side of the cell are we hitting. We know which cell we have hit, so we can find its midpoint. and we know where we have hit, so we can create a vector between the two. We can use the arctangent function to work out which quadrant of the cell have we hit, because this will give us a result which is towards minus pi that way and towards plus pi that way. But in this case, knowing which quadrant still doesn't help, because we've still got a vertical component in one part of the quadrant and we've still got a horizontal component in another part of the quadrant. Now, and only because this is a unit square, we can rotate this axis to line up with the diagonals of the cell. So instead of taking an angle straight up in this case, if we take an angle like this, we can see that we get each edge of our unit cell in its own quadrant. So we know that this is 0, and now from around here we've got our minus pi, and this way we've got our plus pi. In fact, that goes all the way around. So this point is pi over 2, and this point is pi over 2. We can use the result of a slightly rotated arctangent function to work out which side of the cell has been hit, because the arctangent function will give us a one-dimensional variable along this minus pi to plus pi path, and we can directly equate what that value is to which side of the cell, i.e. which quadrant does it lie in. And once we know which quadrant that the collision has occurred in, then we know which value to take as the sampling value for the texture. So if it's in this quadrant, it's x; if it's in this quadrant, it's y. Here, minus x and minus y.
So far we've only considered sampling the texture in one direction, in this case horizontally across the texture. How do we handle vertically? Well, that's much simpler.
Because this is a pseudo 3D application, there is no such thing as vertical, it's just it's a hack. And so if I draw in the world coarsely here, so we've got sort of we're looking down towards, this is a unit cell here and this is a unit cell across, so I'll just label those so you can see which is which. So far we've been working out the columns, and we've been using the distance from where the player is standing to the first obstacle to give us the depth on the screen, and that effectively gives us the value of this pinch between the top of the screen and the bottom. Let me just illustrate that a bit more clearly. The depth to the obstacle really gives us this distance here, which in our implementation is exactly the same as this distance here. As we're drawing each column, we use this depth value to decide when and where to start drawing the walls. And so let's, for example, say starting at the bottom, we know that if we're within that distance, then we're just drawing floor for this row. But when we get above that distance, we're then going to be drawing the wall. And when we get outside of the wall, we're just drawing the ceiling. So given that we know this location and this location in screen space, and we make the assumption that if you can see the wall, it is going to be 1 unit high, then we can take our y sample coordinate, in this case our height, quite easily, because it's just this distance here, 0 to 1. So let's start putting this into code. The first thing I'm going to do is load my sprite wall, which I'm going to do in the onUserCreate function. And I'll do it after I've created my map. I just load the file directly.
Just a little reminder, I don't always do error checking because it can make the code a little bit more bloated than it needs to be, but you should do error checking.
Now I've loaded the sprite, it's time to amend our collision detection routine for when the ray hits a wall. Well, in the original code we used to try and do some little hack to work out was the ray near a corner or not, and it could texture the corner. That gives us the black vertical line showing us the individual cells. We're not going to need that anymore, so all of that can go. What we will leave in is the hit wall. When a cell is hit, I can use its coordinates to determine a midpoint for the cell, because all of my cells are unitary in size, they're 1 by 1. So the middle of a cell must be whatever its integer coordinate is plus 0.5. Now we would only be at this location if a collision has occurred, so I can assume that the distance to the wall is currently the collision point. And I will use the distance to the wall and the player angle, which in this instance is represented through this I vector, to give me some test points. So this is the point where the collision has occurred. Now I've got the location of the middle of the cell that I've hit, and the location of the point of collision, I want to work out the angle between those 2 points. So I can assume there's a vector drawn between those 2 points. What is its angle? And I'll use the atan2 function to calculate this for me. And I just simply give the distances in. So in this case, the first parameter is the difference between the y coordinates, and the second parameter is the difference between the x coordinates. And the atan2 function is nice because it'll handle sort of all the corner cases and caveats with usually trying to work out gradients. Now I know which angle, I effectively know which quadrant the collision has occurred in. But I need to rotate this quadrant by pi/4. Because don't forget, that gives me a single edge of my unit square within that quadrant, rather than sharing a couple of edges within that quadrant. And so once I can determine which quadrant, I can determine which set of the collision coordinates do I need to use in order to calculate my sampling point across the texture. So it's always going to be sample x, i.e. the horizontal sampling distance across the texture, but this is based upon a different coordinate space, and we're trying to work out, do we need x or y coordinates to do this? And of course there are 4 quadrants, so there are 4 possibilities. And I'll just add in a floating point sample x variable. So this is how far across the texture are we going to sample the point. In the original code, the walls were shaded according to intensity depending on how far away they were. We used the different types of pixel blocks to shade accordingly, 50%, 75%, 25%, etc. We don't need any of this now, so that can go. So for the column that we're currently operating on, we now know where the ceiling is and where the floor is. So as we iterate row by row down the screen, we draw accordingly. So for the ceiling, we're just going to draw a black space. If we're between the ceiling and the floor, then we're obviously drawing the wall, which we'll come back to in a second. And if we're not drawing ceiling or wall, then we must be drawing floor. And in the previous code, again, we shaded it according to how far away the floor was from us. We're not going to do that anymore. Instead, we're just going to shade it dark green. So I'm going to get rid of all of this code and just draw a dark green pixel. So we know it's the wall that we want to do some sampling in. And we've got our sampled x coordinate. We've just calculated that through the quadrants. We just now need to calculate the sampling y coordinate, which is simply the percentage distance of the row that we're on between the ceiling and the floor values. And once we've got our 2 sample coordinates, then we can use them to sample the correct glyph and the correct colour for that location, and use the draw routine to draw them to the screen. Let's take a look. Well, straight away we can see we're starting to see some sort of texture on the walls. But it looks a little messy. Also, walls which are very far away get sampled oddly and look quite strange. To get rid of the problems in the distance, I'm just not going to draw any wall if it's too far away. So instead of drawing a wall sample, I'm just going to draw a solid pixel, and it's going to be black. The second problem is a resolution problem. Our step size is quite large. I'm going to just make this a much smaller step size. Now this will reduce the computational efficiency of the algorithm, but I think the end result might be cosmetically and aesthetically better. So now we can see walls that are far away don't get drawn. Okay, this introduces pop-up, which was a problem in older games. What's nice now is we actually get perspective automatically. But there are still some problems with the texture sampling. And we can see at certain distances the textures are just not sampled correctly at all. And this is because the routine that we've created can supersample, i.e. it can make a texture very big quite easily, but it can't subsample. And we might leave that as a topic for a future video. And that's not because subsampling is particularly difficult, but it's because the console mode, which I use to draw all of this, can't really merge colours and symbols together very well. We didn't see great effects with the webcam at the command line video. And ideally what we'd want to see is, as the texture shrinks down, that the individual pixels get merged together a little bit. Something we can't readily do. That said, I think the 3D effect is now quite compelling because the textures offer a lot more perspective.
Now I've chosen just a simple wall texture, and wherever there's a hash symbol in my map, it uses the wall texture. It doesn't need to use the wall texture, we could use a different symbol and choose a different texture accordingly. But I think for now I'm done with drawing the map. Let's draw objects within the game itself, so we might be able to have enemies chasing us, we can have collectibles and bullets and things for a future version of this game.
Of course, if we want more interesting things in the game, then we're going to need to draw some more objects. We're going to have some assets. So I'll use the sprite editor again, and I'll just load up the lamp file that I've already created. You don't need to watch me drawing sprites. And the idea is to try and create something which is radially symmetrical. It doesn't matter what angle you look at it from, it would normally look the same. So columns and pillars and barrels, that sort of stuff. And being radially symmetrical is quite important, because we're going to use a technique called billboarding. And that is, it doesn't matter which direction the player is looking. Because it's radially symmetrical, we can just draw the cross-section of the object. So if the object is also over here, the player is looking at it, we just draw the cross-section. For objects that aren't radially symmetrical, then we would have sprites that represent different cross-sections from different angles. And we would need to choose which one to draw accordingly, depending on the relationship between the object and where the player is currently stood.
But as has been shown many times on this channel, I'm rubbish at drawing, so radial symmetry it is.
We're going to draw objects after we've drawn the background scenery. So I'm going to draw in some field of view lines here, which have been used to draw the background scenery, so the walls and the grass and the sky as necessary. And so the first thing to check is, can the user see the object? i.e., does the object lie within the user's field of view and within sort of an acceptable distance? Well, in this case, yes, it does. We then need to calculate which column of the screen represents the middle of our object. So we're basically getting our x-coordinate in our field of view. And then we want to scale the height of the object and put it back into the screen according to the distance away from where the player is. So we're going to do many of the same calculations we've already done for calculating walls, but we can do them on a per object basis. So I'm going to maintain a list of all of the objects that are in the game. I've created a structure which is a simple object, and all this structure contains is the x and y coordinate of where that object is in our 2D map, and a pointer to the sprite used to draw the object. And given that my sprite is a lamp, I'm going to also need the sprite loading in, so we'll have to change our onUserCreate function to do just that. Let's load in the lamp, and I'm going to populate my list with a few predefined lampposts. I'll just use a static initializer to do this. So I'm going to specify one lamppost to be at 8.5 by 8.5 and tell it to use the sprite lamp. And you might be wondering why 0.5 and 0.5? Well, that will place it in the middle of our cells because they're in unit space. Let's create a couple of more lampposts. We'll have 7.5 and 7.5 and 10.5 and 3.5. So we've got two which are close to each other and one which is in the corner somewhere. All of our object drawing is going to occur after we've drawn the background, but before we display the map. I'm going to use a for loop with the auto keyword to go through every object in the list. I first need to evaluate, can the object be seen by the player? And the first thing I'll need to do then is calculate, is it within an acceptable distance? So I just use Pythagoras' theorem to calculate this. The second thing to calculate is the object within the player's field of view. So we know that the angle the player is looking at, and we can create a vector from the player's feet to the object, and so if that angle is within the field of view angle, then we reckon that the object can be seen by the player. If we take this object, for example, that angle does not lie within the green field of view angle here, so it can't be seen. It may be the case that we have a situation like this, where the object will pop in from the side. I'm not going to worry about that for now. So if we know the object is radially close enough to the player to be seen, we can check, is it within the field of view, the arc? And I'm going to use the subtraction of two atan2 functions to give me the angle between two vectors. And you need to do a little bit of bodging of that number to give you a result between 0 and 2 pi. And so all I need to do ultimately is compare the angle of the object away from the player to the field of view that I've set up for drawing the screen. And as long as the angle is within the field of view, it's good. We're good to draw it. And because drawing is costly, we should use these flags to determine whether or not we should draw the object. I've also made a clause here which means we don't draw things that are too close to the player. And this is a little trick that satisfies two things. Firstly, it gives the player a sense of body, a sense of actually existing within the world.
And secondly, it stops all sorts of nasty asymptotic errors as the distance from the player to the object approaches 0.
Since we know the distance from the player to the object, we can work out where the object's floor and where the object's ceiling is, just as we did for the walls. And if we know the floor and the ceiling, we can work out the height of the object. Because as the object is further away, it's going to look smaller. And once we know the height of the object, we can calculate the width of the object using the aspect ratio of the sprite. Because the sprite's dimensions don't change, but the only one that we can calculate is the height. So we need to use the height, the aspect ratio, to determine the width. And because we know the angles, the distances, and the field of view, and the screen widths, we can calculate where the object is across the screen.
Because don't forget, we're not working on a column by column basis anymore now. We've finished drawing the background and doing the ray tracing.
The object width and object height variables are in screen space, and so for all of those affected pixels on the screen, we need to draw the appropriate pixel of our texture. So I've created two little for loops which iterate over the object width and object height. To sample the texture, we need to sample in normalized space, which, well, that's simple enough. It's just taking the position of the object width divided by the object width, so we're getting a percentage. And firstly, we'll sample the glyph, so which symbol should we use? And I'm going to create a variable which represents the distance across the screen that our object is currently occupying. So it takes the middle of the object plus the current column we're working with and offsets it by the object width divided by 2. Just to make sure nothing nasty is going to happen with this number, I'm going to make sure it's within bounds, so is it greater than or equal to 0 and less than the width of our screen, and if it is, then I'm going to draw the pixel to the screen. Using the column as the x-coordinate. We know the y-coordinate because that's our object ceiling plus how far we're iterating down the screen in our loop. We've got the character already because we've sampled it. And I'm going to specify the colour. I'm going to sample it directly here. You might think, why have I not done this separately? But that will become clear in a couple of minutes. Let's take a look. Well, we can see we've now got some objects in the game, but they look a little strange. And we'll try always look at these things from different angles, just to make sure we understand what's going on. And what we can see is actually, well, even though they're always facing us, because they're radially symmetrical billboards, they're not quite right. Things are drawn behind objects. We shouldn't be able to see one of those lamps there. Also, what are these big black borders around the object? Can be improved. Also, it looks like the objects are drawn irrespective of the distance. But, conveniently, they are drawn sort of in the right location according to the field of view. And they do have a 3D presence about them. Well, the black boxes around the objects are simply because we're not taking into account transparency within our sprite. So I'm not going to draw a pixel if the sprite is equal to an empty space, which has become the console game engine sort of notation for transparent pixel. So let's take a look at that. Perfect, so that's now given us the proper transparency effect for the sprites. However, we shouldn't be able to see sprites behind walls. We now need to add our first genuine 3D component, a depth buffer.
The depth buffer is an array of floats that represent the distance from the player to the walls. We're going to record that for every single column. So far we've just been throwing that information out once we've drawn the column because we don't need it anymore. But now I'm going to retain it, so when we draw objects we can compare with the depth buffer of the walls. And if the object is further than the depth buffer of the wall, then clearly the wall is in front of it. So we don't want to draw that column of the object.
Let's start by adding a depth buffer variable and initializing it in onUserCreate. And I'm just going to initialize it with the number of columns that we've set up as part of the construct console. Actually populating the array is not very difficult because we already know the depth, we know the distance to the walls as part of our rendering calculations. So I'm just going to store them. And this of course is updated every frame. Now we just previously changed this routine to not draw if the pixel is set to transparent, but we can also add to this another clause which means we only draw the column if the object is closer than the depth for that column in the depth buffer. So let's take a look. You see our lamps again. I'll go and stand behind this corner of the wall to make sure. Oh, perfect. There we are. Straight away we can see now that our lamps, I keep forgetting I've implemented strafe, our lamps are now obscured accordingly by the wall. Now it may look like the lamps also obscure each other here, but this is nothing other than a coincidence. In fact, if I go to this side, we can see it doesn't work at all. And that's because we're not modifying the depth buffer based on objects. That's actually quite complicated to do in this framework, and I'll leave it for the next video. There will be another part to this series. There is a simple fix we can do here to help. We can update the depth buffer with the distance for that column of the object. However, this will have one little undesirable artifact. And we can take a look, and that is the transparency won't work quite correctly. But I think it looks better than drawing the objects on top of each other in the correct order.
I think it's finally time to add some shooting to our first-person shooter, so let's add some rudimentary bullets.
Well, of course, again, I'm going to need an asset, so I've created a sprite here which represents a fireball, something that's going to be drifting through the maze. And since I've another type of sprite, I'll create another sprite variable and load it in the onUserUpdate function. I've called it fireball. But I'm also going to make a small change to our object. Since we've got a nice routine for drawing objects, I'm going to try and use our object structure in place, so we don't need to change too much. But if we want to add sort of physics and dynamics, and we do for bullets because they're going to be moving around the screen, then I'm also going to store the velocity components of a velocity vector, which is going to be simply Vx and Vy. I'm also going to store a boolean to say whether the object should be removed or not. And that's because we don't want hundreds of objects. Bullets need to die at some point, and the rule in my game is if the object ever goes within the boundaries of a cell, so if it ever enters a solid cell, then it's going to get removed. Since we've changed the structure, we also need to change our initializer list. Now the lamps don't move around, so we'll set their velocities to 0. And we never want to remove them either, so we'll set that to false. I've not added any bullets to the list. We'll do that when the user presses the spacebar. Well, every time the user releases the spacebar, we're going to create a new object. And the immediate position of the object is going to be the player's position. The bullet originates from the player. We know the player's orientation because we store the player angle variable, but I'm going to add some noise to it, so the bullets don't all just fire off in a perfect straight line, they fire with a little bit of deviation. This just makes it nicer to look at. I'm going to initialize the sprite of the object to the fireball. I'm going to set its remove flag to 0, and I'm going to add it to the object list. Now before we do any checks to see if the object can be seen, I'm going to update its physics, and this is a very simple operation because it's just going to be the position is updated by the velocity times the f-elapsed time, which we've seen in many other videos. But I'm also going to check that if the position of the object is a cell, if it's solid, then I'm going to set its remove flag to true. And the reason I'm doing this is it's quite tricky to remove things from vectors and lists, so I'm just going to set it to true and we'll basically garbage collect it later on. And in fact we can do that very nicely simply before we display the map. I can use the remove if function and a little tiny lambda function to remove all of the objects where the remove flag is set to true. And so now if I run it and release the spacebar, we can see an object moving with velocity away from the player. In fact, if I fire lots of objects, let's not crash into the wall, let's go into an open space, fire lots of objects and strafe, and we can see, yes, there's stuff happening. It kind of works. And when they hit the walls, they disappear.
And so there you have it, a quick update to the command line first-person shooter engine. I think it looks much better now with textured walls and the potential to have objects. I think using some of the pathfinding algorithms that we've created, and maybe some of the maze generating algorithms, there's the basis for a real little game here. Anyway, a quick reminder that if you've been inspired by any of the videos on this channel and would like them featured in a video just before probably Christmas time, please submit some code or a video or a link to anything to this email address, please, showcase2017@onelonecoder.com. And as always, for this video, the source code is available on the GitHub repository. Please take it, hack it, do what you want with it, have some fun with it. If you've enjoyed this video, big thumbs up, does wonders for my self-esteem. Have a think about subscribing, and I'll see you next time. Take care.